A world exists that orbits no star. Its surface, colder than anything you can imagine, receives no warmth from a distant sun. Deep beneath frozen layers measured in kilometers, residual heat from a violent birth billions of years ago might sustain something we'd hesitate to call life. This planet has been traveling through the void for longer than Earth has supported complex organisms, and recently, astronomers detected one of these wanderers closer than we've ever confirmed before. Rogue planets represent one of astronomy's most unsettling discoveries. These aren't comets or asteroids. They're full-scale worlds, some larger than Jupiter, drifting through interstellar darkness without gravitational allegiance to any star. Until recently, we assumed planets required stars. The very definition seemed to demand it. Then observations started revealing something unexpected. The galaxy is absolutely crowded with these orphaned worlds. The numbers are staggering in ways that fundamentally challenge our understanding of planetary demographics. The Milky Way might contain 8 trillion rogue planets. Let that settle for a moment. 8 trillion. Our galaxy has roughly 400 billion stars, which already seems incomprehensible. But for every star burning in the night sky, there could be 20 planets wandering alone through the darkness between stellar systems. On January 2, 2026, an international team announced they discovered a new rogue planet about 9,800 light-years from Earth. What makes this detection revolutionary isn't just that they found another wanderer. For the first time, astronomers obtained a direct mass measurement, not a statistical estimate based on probability distributions. They know for certain this object has a mass similar to Saturn. The discovery came through a microlensing event with the rather unglamorous designation KMT 2024 BLG 0792/OGLE 2024 BLG 0516. Multiple telescopes on the ground and in space watched simultaneously as this dark world passed between Earth and a distant background star, its gravity bending light in ways that revealed its presence and properties with unprecedented precision. But here's what keeps astronomers awake. We're only detecting the largest ones, and even then, only when they happen to pass directly between us and another light source. The smaller rocky worlds, the planets that might resemble Earth or Mars, remain completely invisible with current technology. They emit almost no infrared radiation, reflect no starlight, and only reveal themselves through gravitational effects that require extraordinary luck to observe. Think about the implications. Every planetary system that forms goes through a violent settling period. Computer simulations tracking the formation of 100 different solar systems, each containing 3 to 10 planets orbiting a sun-like star, revealed something disturbing when researchers let the equations run for 1 billion simulated years. For every stable system like ours that emerges, at least one gas giant gets ejected into interstellar space. And 5 to 10 smaller, rocky worlds get flung out alongside it. Our own solar system might have participated in this cosmic exile program. Some researchers theorize we once had a 5th giant planet alongside Jupiter, Saturn, Uranus, and Neptune. During a chaotic period called late instability, gravitational interactions between these massive worlds became unstable. The unfortunate 5th planet got accelerated to escape velocity and vanished into the dark. With the survivors, the planets that happened to find stable orbits after the violence settled. The ejection mechanisms are diverse and brutal. In systems with 2 stars orbiting each other, planets can get caught in gravitational tug-of-war scenarios that eventually tear them free. When stars pass unusually close to each other in wide binary systems, the orbital dynamics can shift so dramatically that planets get stolen or ejected entirely. But the most common mechanism is simpler and more direct: planet-planet scattering. Picture 2 planets whose orbits bring them too close. The gravitational interaction becomes chaotic. One planet, usually the less massive of the two, gains enormous orbital energy in a single encounter. Within a few orbits, it's moving fast enough to break free from the star's gravity entirely. The other planet settles into a more stable orbit, its trajectory only slightly altered. One world continues its predictable life. The other begins a journey through darkness that might last billions of years. These ejected planets retain velocity signatures that tell their origin stories. Astronomers measure something called velocity dispersion, essentially how fast these objects move relative to surrounding stars. Rogue planets kicked out through planet-planet scattering travel at 8 to 16 kilometers per second. Those ejected through binary star interactions move 3 times faster. These velocities serve as fingerprints, revealing the violence of their exile long after the event occurred. Not all rogue planets started their existence orbiting stars. Some formed alone in interstellar space, condensing from clouds of gas and dust through processes more similar to star formation than traditional planet formation. These objects collapse under their own gravity, accreting material directly from surrounding nebulae, but never gathering enough mass to ignite fusion and become true stars. The International Astronomical Union proposed calling them sub-brown dwarfs to distinguish them from planets that formed in protoplanetary disks and were subsequently ejected. The distinction matters because it reveals fundamentally different formation pathways. An ejected planet carries with it the chemical signature of the stellar system where it formed. Its composition reflects the specific mix of elements present in that particular protoplanetary disk. A planet that formed alone in interstellar space would have a completely different chemical profile, one that reflects the average composition of the interstellar medium rather than a specific stellar environment. In 2025, astronomers observed something that challenged previous assumptions about these isolated worlds. They found a rogue planet designated CHA 1107 to 7626, located about 620 light-years away in the constellation Chameleon. This object has a mass 5 to 10 times that of Jupiter. But what stunned researchers was watching it actively accrete material from a surrounding disk of gas and dust at a rate of 6 billion tons per second. This represents the strongest accretion episode ever recorded for a planetary mass object. The discovery revealed that some rogue planets can exhibit star-like behavior during formation, with magnetic activity driving material infall in ways previously thought exclusive to stellar evolution. The planet is still forming, still growing, still pulling in matter from its environment despite having no parent star to organize that material into a traditional protoplanetary disk. Detecting these objects requires monitoring millions of stars continuously, watching for the brief moments when a rogue planet's gravity bends light from a background source. The technique, called gravitational microlensing, works because even planets have enough mass to warp spacetime according to Einstein's general relativity. When alignment occurs, the background star brightens temporarily, sometimes for just a few hours. The challenge is enormous. Only one star in 100,000 gets microlensed at any given time. To find planets, you need to observe millions of stars on timescales of several minutes, checking at least several times per hour. Survey teams aim their telescopes towards Sagittarius, which lies in the direction of our galaxy's dense center where about 400 million detectable stars cluster together. Even then, hundreds of events per year toward the galactic bulge still represent a tiny fraction of the actual population. The upcoming Nancy Grace Roman Space Telescope, scheduled to launch by May 2027, should revolutionize this field entirely. Scientists expect it will discover at least 400 more rogue planets, potentially several thousand. The telescope can image the entire sky 1,000 times faster than Hubble, using both microlensing and direct infrared imaging to find worlds potentially as small as Mars. But here's the question that shifts this from purely academic interest to something more immediate. What happens if one of these wanderers enters our solar system? The odds are extraordinarily low. Astronomers calculate roughly 1 in 1 trillion chance within the next 1,000 years. Space is vast enough that even with trillions of rogue planets wandering the Milky Way, the distances between objects make close encounters vanishingly rare. Yet the theoretical consequences are worth understanding because they reveal just how delicately balanced our solar system actually is. If a rogue planet approaching 13 times Jupiter's mass crossed into our solar system, the gravitational disturbance would begin long before any visible approach. Our planets orbit the Sun in relatively narrow bands we call the habitable zone, regions where conditions remain stable enough for liquid water and predictable seasons. Earth sits comfortably within this zone, neither too close to freeze nor too near to burn. But that comfortable position depends entirely on gravitational stability maintained over billions of years. The intruder would warp that stability immediately. Its gravitational field would reach outward like invisible fingers, tugging on objects billions of kilometers away. Neptune would feel the pull first, its orbit shifting microscopically at first, then more dramatically as the rogue planet advanced inward. Uranus would follow, then Saturn, then Jupiter. Each giant planet's orbit would stretch, becoming more elliptical, less circular. The perfectly synchronized dance that has kept our solar system stable since its formation would begin breaking down. Earth's orbit would change too. Not necessarily in ways that eject us from the habitable zone entirely, but in ways that fundamentally alter how we experience seasons and climate. Picture our planet's orbit stretching into an elongated ellipse. For part of the year, we'd swing closer to the Sun than we've been in 4 billion years. Temperatures would spike dramatically during these brief summers, potentially reaching levels that make current heat waves seem mild. Ocean surfaces would heat rapidly. Ice caps would melt at accelerated rates. Weather patterns would destabilize completely. Then the orbit would carry us outward again. These winters would last far longer than the summers, plunging Earth into extended cold periods that could span years or decades depending on the severity of orbital disruption. Agriculture would collapse almost immediately. Crops require specific growing seasons, predictable temperatures, stable water cycles. When summer lasts only a fraction of its normal duration, and winter extends indefinitely, food production becomes impossible at scale. Within a single orbital period, humanity would face resource shortages unlike anything in recorded history. But orbital disruption represents just one category of threat. The rogue planet's passage would also destabilize the asteroid belt between Mars and Jupiter. This region contains millions of rocky bodies, most following stable orbits that keep them safely distant from inner planets. Gravitational perturbation from a massive intruder would send countless asteroids careening in unpredictable directions. Some would fall toward the Sun. Others would be flung outward into deep space. And some would find trajectories that intersect with Earth's orbit. The bombardment wouldn't happen all at once. Instead, we'd face an extended period of elevated impact risk lasting potentially thousands of years as the disturbed asteroid population gradually restabilized. Each impact would carry consequences proportional to the impactor's size. Small asteroids would burn up in the atmosphere or create localized damage. Larger ones would generate regional devastation. And the largest could trigger mass extinction events comparable to the impact that ended the dinosaurs 66 million years ago. The outer solar system would experience even more dramatic effects. The Kuiper Belt and Oort cloud contain trillions of icy bodies, most in stable distant orbits that keep them far from the inner planets. These regions function as cosmic deep freezers, preserving pristine samples of material from the solar system's formation. When a rogue planet passes through, it doesn't just disturb a few objects. It reorganizes entire populations, sending waves of comets toward the inner solar system. Historical records show that even minor perturbations in the Oort cloud can increase comet activity measurably. A full-scale disruption would unleash a comet storm lasting millions of years. The night sky would fill with visible comets, dozens at a time, their tails stretching across the heavens. Beautiful from a distance. Terrifying when you realize each represents a potential impact threat moving at tens of kilometers per second. Yet direct collision with the rogue planet itself would dwarf all these other scenarios. The kinetic energy involved defies comprehension. A Jupiter-mass object moving at typical interstellar velocities, somewhere between 50 and 200 kilometers per second, carries momentum that makes terrestrial disasters seem insignificant by comparison. If Earth happened to lie directly in its path, the collision wouldn't just destroy our planet. It would vaporize it completely. The impact would release more energy than all nuclear weapons ever built, multiplied by billions. Both worlds would transform instantly into expanding clouds of superheated plasma, temperatures reaching millions of degrees, hot enough to strip electrons from atoms. The debris cloud would glow brighter than the sun briefly before beginning its long cooling process. Over millions of years, this material might eventually coalesce into new bodies. But nothing resembling Earth would remain. No fossils. No geological record. No evidence that our planet ever existed beyond chemical signatures in the debris field. The probability of such a direct collision remains vanishingly small. Space is vast. Even within our solar system, the distances between objects dwarf the sizes of the objects themselves. A rogue planet could pass through the solar system and miss every planet purely by chance, simply because empty space dominates the architecture. The odds of threading the needle to hit Earth specifically are so low that astronomers calculate perhaps one such event per trillion years. But near misses carry their own dangers. The rogue planet doesn't need to hit Earth to devastate it. A close approach, even one that misses by millions of kilometers, would generate tidal forces powerful enough to stress our planet's interior. Imagine Earth's entire mass being pulled unevenly, the near side attracted more strongly than the far side. This differential force, called a tidal gradient, can trigger geological activity on unprecedented scales. Volcanic eruptions would increase in frequency and intensity as the planet's mantle convects more vigorously under tidal heating. Earthquake activity would spike globally. Tectonic plates would shift more rapidly than normal, potentially triggering mega-earthquakes that make the most powerful historical quakes seem minor. Coastlines would experience massive tsunamis as ocean water responds to the changing gravitational field. The planet wouldn't tear apart, but it would experience geological violence concentrated into a brief period rather than spread across millions of years. Then there's the Moon. Our natural satellite orbits at a distance where Earth's gravity dominates, but that dominance isn't absolute. A massive object passing nearby could perturb the Moon's orbit significantly, potentially even capturing it entirely if the geometry aligned precisely. Losing the Moon would alter Earth's axial tilt over time, destabilizing climate patterns that depend on that tilt remaining relatively constant. Tides would weaken dramatically, affecting ocean circulation patterns that regulate global temperature distribution. Research into these scenarios isn't purely academic. Scientists study them to understand the limits of planetary system stability, the frequency of catastrophic events over cosmic timescales, and the resilience of life under extreme conditions. The models they build require simulating gravitational interactions between multiple massive bodies over millions of years, tracking how small perturbations compound into large-scale reorganization. These simulations reveal something crucial about our solar system's architecture. The current configuration isn't random. It represents the stable endpoint of billions of years of gravitational evolution. Early in the solar system's history, planetary orbits were far less regular. Planets migrated inward and outward. Some collided. Others were ejected entirely. The NICE model, named after the French city where researchers developed it, suggests that our gas giants once occupied completely different orbital positions before gravitational interactions shuffled them into their current locations. That early chaos may have ejected a fifth giant planet entirely. Computer models show that systems starting with 5 gas giants tend to eject one, leaving 4 in stable orbits that match what we observe today. If true, our solar system has already experienced the kind of gravitational violence that creates rogue planets. We may have contributed to the population of wanderers drifting through the galaxy. Somewhere out there, a Jupiter-sized world might be traveling alone through the darkness, carrying with it chemical signatures that would identify it as having formed in our solar system billions of years ago. Understanding rogue planet encounters also helps astronomers estimate how common such events are throughout the galaxy. If systems typically eject multiple planets during formation, and if billions of systems have formed over the galaxy's lifetime, then trillions of rogue planets represent a natural consequence of planet formation itself. The process is violent and chaotic, with only a fraction of formed planets remaining gravitationally bound to their parent stars. That chaos produced something else beyond ejected planets. It created a testing ground for understanding how gravitational interactions scale across different masses and distances. When astronomers model rogue planet encounters, they're not just calculating abstract trajectories. They're mapping the boundaries between stability and catastrophe, between systems that endure and systems that disintegrate. The math reveals patterns that hold true regardless of scale, from moons orbiting planets to planets orbiting stars to stars orbiting galactic centers. These patterns explain why certain orbital configurations persist while others collapse rapidly. Resonances matter enormously. When 2 orbits have periods that form simple ratios, 3:2 or 2:1, the bodies repeatedly align at the same points in their orbits. These alignments accumulate gravitational nudges that either stabilize the system or destabilize it, depending on the specific geometry. Jupiter and Saturn demonstrate this principle. Their orbital periods nearly form a 5:2 ratio, close enough to create significant long-term effects but far enough from exact resonance to avoid catastrophic instability. A rogue planet passing through disrupts these delicate balances. Even a relatively distant encounter can perturb orbital periods enough to shift a stable resonance into an unstable one. The effect cascades. Jupiter's orbit changes slightly. That alters its gravitational influence on Saturn. Saturn's shifted orbit affects Uranus. The inner planets feel the effects later but inevitably. Over thousands or millions of years, orbits that appeared stable reveal themselves to be metastable, waiting for a trigger to push them into new configurations. This vulnerability explains why finding rogue planets matters beyond academic curiosity. Each discovery provides data points for estimating encounter frequencies. Astronomers can calculate how many rogue planets exist within certain distance ranges, how fast they typically travel, and therefore how often close approaches occur statistically. The numbers suggest that over the lifetime of a typical planetary system, at least one moderately close encounter with a rogue planet is more likely than not. But what constitutes close in cosmic terms? A rogue planet passing within 1 light-year would have minimal effect. At that distance, even a massive interloper exerts negligible gravitational influence over the brief time it takes to pass. Move that encounter to within 100 astronomical units, roughly 3 times Neptune's orbital distance, and the story changes. Now the rogue planet spends years or decades within the outer solar system's gravitational sphere of influence, plenty of time for orbital perturbations to accumulate. The difference between a harmless distant passage and a system-disrupting encounter comes down to velocity and trajectory. A fast-moving rogue planet on a perpendicular trajectory might slice through the outer solar system in just a few years, limiting the time available for gravitational interactions. A slower object on an aligned trajectory could remain gravitationally engaged for decades or centuries, maximizing the cumulative perturbations. The geometry matters as much as the mass. Detecting such an encounter in advance presents technological challenges that current capabilities barely address. Rogue planets emit almost no light. They don't reflect starlight because they're not near stars. Their thermal emission peaks in infrared wavelengths, but even then, a Jupiter-mass object several hundred astronomical units away would appear incredibly faint. Current surveys might detect it a few years before closest approach, not the decades or centuries that would allow meaningful preparation. That detection gap creates an uncomfortable situation. We know rogue planets exist in large numbers. We understand the potential consequences of close encounters. Yet we have no systematic early warning system capable of identifying incoming objects with sufficient lead time. The upcoming Nancy Grace Roman Space Telescope will improve this situation dramatically. Scheduled to launch by May 2027, it will conduct the Galactic Bulge Time Domain Survey, potentially discovering hundreds to thousands of rogue planets and refining mass estimates across the population. Roman's capabilities extend beyond simple detection. By observing microlensing events where rogue planets pass in front of background stars, astronomers can measure not just presence but mass with unprecedented accuracy. The January 2026 discovery of a Saturn-mass rogue planet roughly 9,800 light-years away demonstrated this technique's power. For the first time, researchers obtained a direct mass measurement rather than statistical estimates. That single data point improved population models significantly. More discoveries like that one will paint a clearer picture of the rogue planet population structure. Are most ejected worlds small rocky planets, or do gas giants dominate? Do formation mechanisms leave distinctive signatures in the mass distribution? How does ejection velocity correlate with planet type? These questions matter for risk assessment. A galaxy filled with Earth-mass rogues presents different statistical risks than one dominated by Jupiter-mass wanderers. The former are more numerous but less gravitationally disruptive. The latter are rarer but capable of greater orbital perturbations. Understanding the population structure also illuminates planet formation physics. Computer simulations suggest that for every solar system like ours, at least one gas giant and 5 to 10 smaller rocky worlds get ejected during formation. Those numbers come from modeling hundreds of systems with varying initial conditions, then running the physics forward for billions of simulated years. The simulations consistently show that ejection isn't occasional. It's standard. Most planetary systems shed members during their chaotic early evolution. This raises a peculiar question about our own history. If ejection is standard, did our solar system expel worlds during its formation? The NICE model suggests yes. Named after the French city where researchers developed it, this model proposes that our gas giants once occupied different orbital positions. Gravitational interactions shuffled them into their current locations, potentially ejecting a fifth giant planet entirely in the process. Evidence supporting this scenario includes the orbital distributions of asteroids and comets, the late heavy bombardment that scarred the Moon roughly 4 billion years ago, and the unusual orbits of certain Kuiper belt objects. If we did eject a planet, it's out there somewhere. It would carry chemical signatures linking it to our solar system, isotopic ratios that formed in our protoplanetary disk. Finding such an object would confirm the NICE model directly and demonstrate that even stable-appearing systems like ours experienced violent gravitational upheavals. The search for our hypothetical lost sibling represents one of astronomy's more speculative pursuits, but improving detection methods make it incrementally less impossible. Meanwhile, the search for Planet 9 continues. This hypothetical massive planet in the outer solar system could explain the peculiar clustering of certain trans-Neptunian object orbits. These extreme objects, orbiting beyond Neptune at distances averaging more than 250 astronomical units, tend to make their closest solar approaches in one sector. Their orbits tilt similarly. Random distribution would spread them more evenly. Something massive appears to be shepherding them gravitationally. Planet 9, if it exists, would have a mass roughly 10 times Earth's and orbit about 20 times farther from the Sun than Neptune. Several formation scenarios could produce such an object. It might be the core of a gas giant that Jupiter ejected during the solar system's youth. It could be a rogue planet that our Sun captured from interstellar space. Or it might have formed on a distant orbit and been pulled into its current eccentric path by a passing star. The capture hypothesis particularly intrigues researchers. Studies show that the Sun's gravitational field, combined with galactic tidal forces, creates regions where passing objects can become permanently trapped through a mechanism called permanent weak capture. An interstellar object entering these zones might remain on a chaotic orbit for millions of years before settling into a stable configuration. The Sun could potentially collect passing rogue planets and hold them at the solar system's outskirts, occasionally trading them with neighboring star systems like Alpha Centauri. This capture mechanism depends on precise conditions. The incoming object needs the right velocity and trajectory to dissipate enough orbital energy without escaping entirely. Galactic tides help by subtly altering the object's motion as it travels through regions where the Milky Way's gravitational field varies. These variations are tiny, but over millions of years, they can shift an initially unbound orbit into a bound one. The process works in reverse too, potentially releasing captured objects after long periods of gravitational confinement. Whether Planet 9 is a captured rogue or a native object, finding it would answer fundamental questions about solar system architecture. The Vera C. Rubin Observatory, currently under construction in Chile, should either detect it or rule out its existence within a few years through comprehensive sky surveys. The observatory's wide field of view and sensitive detectors will image the entire visible sky repeatedly, tracking anything that moves against the background stars. If Planet 9 lurks out there, Rubin will spot it. That pending discovery or non-discovery represents a broader shift in astronomy. We're moving from an era where we knew our immediate neighborhood reasonably well but understood little about the wider galaxy to one where we're cataloging thousands of exoplanets, detecting rogue planets light years away, and mapping the galaxy's structure in unprecedented detail. Each discovery refines our understanding of how planetary systems form, devolve, and sometimes disintegrate. The technology driving these discoveries has evolved dramatically. Finding rogue planets requires detecting objects that emit virtually no light and reflect nothing from nearby stars. They're invisible in traditional surveys. Microlensing changed everything. The technique exploits Einstein's general relativity. Any massive object warps spacetime around it, bending light that passes nearby. When a rogue planet drifts between Earth and a distant star, it acts as a gravitational lens, briefly magnifying the background star's light. The effect lasts hours to days depending on the planet's mass and velocity. Astronomers monitoring millions of stars can catch these fleeting signals. The practical challenges are staggering. Only 1 in 100,000 stars undergoes microlensing at any moment. Survey teams point their telescopes toward the galactic bulge in Sagittarius, where 400 million detectable stars cluster densely. Even there, finding planets requires observing millions of targets multiple times per hour. The OGLE and MOA projects identified hundreds of candidate events by 2007. Most were stellar lenses, but occasionally a light curve showed the characteristic spike indicating a planetary companion. Coordinated telescope networks spanning the globe enable continuous coverage, preventing observers from missing brief events that occur during daylight hours at any single site. January 2026 brought a breakthrough that refined these techniques dramatically. An international team announced detecting a Saturn-mass rogue planet 9,800 light-years away through microlensing event KMT 2024 BLG 0792. What made this discovery extraordinary was simultaneous observation from ground-based telescopes in space. The parallax measurements from different viewing angles allowed direct mass calculation rather than statistical estimates. For the first time, astronomers knew a rogue planet's mass with certainty. The object weighed approximately 95 Earth masses, placing it firmly in the gas giant category. Previous detections relied on models comparing light curve characteristics to simulations. This measurement established a new standard for confirmation. But mass alone doesn't reveal origin stories. Velocity provides crucial forensic evidence about how these worlds became orphans. Ejected planets retain significant excess velocities, typically 8 to 16 kilometers per second above the background motion of stars in their birth regions. This speed difference acts as a fingerprint. Planets ejected through interactions with binary companions move even faster, roughly 3 times the velocity of worlds expelled through planet-planet scattering. These measurements let astronomers reconstruct the gravitational violence that launched specific objects into interstellar space. Each rogue planet carries evidence of its past encoded in its trajectory. Some rogue planets might never have had parent stars. Isolated formation theory proposes these objects form like stars do, from collapsing gas clouds, but halt at planetary scales. Insufficient initial cloud mass or external disruptions truncate accretion before the object can grow large enough for fusion. Turbulence within molecular clouds generates density perturbations that fragment into multiple low-mass clumps. These cores collect gas directly from surrounding nebulae, building planetary mass bodies without protoplanetary disks. The International Astronomical Union proposed calling such objects sub-brown dwarfs to distinguish them from ejected planets. Whether this distinction matters philosophically or just taxonomically remains debated. Another 2025 discovery challenged assumptions about rogue planet behavior. Astronomers identified CHA 1107 to 7626, located 620 light-years away in Chameleon constellation. This free-floating planet exhibits a mass 5 to 10 times Jupiter's and displays something unprecedented, an enormous growth spurt. The object accretes gas and dust from surrounding material at 6 billion tons per second, the strongest episode ever recorded for planetary mass bodies. This rogue planet possesses its own accretion disk, behaving more like a young star than a typical planet. Magnetic activity appears to drive material infall in ways previously thought exclusive to stellar evolution. The discovery suggests rogue planets can remain dynamically active long after ejection or formation. These findings reveal how violent planetary system formation actually is. Computer simulations model this chaos systematically. Researchers created 100 virtual planetary systems, each containing 3 to 10 planets on near-circular coplanar orbits around Sun-like stars. Running the equations forward for 1 billion simulated years produced consistent results. For every stable system like ours that forms, at least one gas giant and approximately 5 to 10 smaller rocky worlds get ejected into interstellar space. The process is standard, not exceptional. Ejection represents a normal byproduct of gravitational interactions during the first several million years when systems haven't settled into stable configurations yet. Binary star systems amplify these dynamics. Planets in binary systems experience more complex gravitational perturbations than those orbiting single stars. Even wide binaries contribute. Passing stars can perturb the eccentricity of stellar orbits, occasionally sending binary companions close together. These encounters trigger planetary ejections or even steal planets from one star's gravitational sphere. Research focusing on circumbinary systems, planets orbiting both stars in a binary, shows that misaligned orbital planes create instabilities ejecting planets with much greater frequency. Given that binary stars comprise more than half of all stellar systems, they likely contribute disproportionately to the rogue planet population. Planet-planet scattering in single-star systems follows predictable patterns. When two planets approach too closely, gravitational interactions transfer orbital energy between them. Usually the less massive planet gains energy, accelerating to escape velocity while its massive companion's orbit shrinks slightly. The exchange conserves momentum but redistributes it dramatically. Close encounters during migration through gas-rich protoplanetary disks can trigger these events. Planets forming in compact configurations face higher collision and ejection probabilities. Our solar system possibly experienced such violence. Some researchers theorize we once had a fifth giant planet alongside Jupiter, Saturn, Uranus, and Neptune during a chaotic period called late instability. Gravitational interactions with other giants would have exiled this unfortunate world. The Nancy Grace Roman Space Telescope, launching by May 2027, will revolutionize rogue planet studies. Its wide field of view images the entire sky 1,000 times faster than Hubble. The Galactic Bulge Time Domain Survey will detect several hundred to several thousand free-floating planets, providing a robust statistical sample. Roman will employ both microlensing and direct infrared imaging, potentially finding planets as small as Mars. Mass measurements from parallax observations will become routine rather than exceptional. Within a few years, astronomers expect to understand rogue planet mass distributions and spatial distributions throughout the galaxy with unprecedented precision. Roman's survey scope extends beyond planets. The low mass range includes ejected planets. Brown dwarfs occupy the middle ground, too massive for planets, insufficiently massive for fusion-like stars. The high end encompasses stellar corpses, neutron stars, and black holes. Astronomers estimate our galaxy contains approximately 100 million stellar mass black holes, but isolated ones remain invisible. Roman's mass-dependent detection method will find them even without nearby matter to illuminate their presence. This comprehensive census of dark objects will reveal the hidden population of massive bodies lurking between stars. How likely is a rogue planet encounter threatening Earth? The odds within the next 1,000 years sit at approximately 1 in 1 trillion. Space's vastness provides protective buffering. Even with trillions of rogue planets wandering the Milky Way, typical distances between objects make close encounters extraordinarily rare. Our solar system occupies a relatively sparse region. Stellar density near the galactic core increases encounter probabilities, but we orbit 26,000 light-years from that dangerous neighborhood. The emptiness between stars shields us far more effectively than any planetary defense system could. But theoretical scenarios illuminate what could happen if one arrived. A rogue planet 13 times Jupiter's mass would gravitationally disrupt every planetary orbit in our system. Earth's path would become more elliptical, carrying us closer to the Sun during perihelion and farther during aphelion. We orbit within the narrow habitable zone where liquid water exists. Increased orbital eccentricity might not push us outside this zone permanently, but it would create extremely short, hot summers followed by prolonged, frigid winters. Compressed growing seasons would devastate agriculture. By the first never-ending winter's end, food shortages could threaten civilization itself. The gravitational architecture would fundamentally transform. Direct collision with Earth would vaporize both worlds, creating debris clouds of molten rock and gas eventually coalescing into new bodies. The kinetic energy from an object moving hundreds of kilometers per second would release energy equivalent to billions of nuclear weapons. Impact temperatures would reach solar surface levels. Any life would be instantly annihilated. More likely, though, a massive intruder would pass through without colliding, scattering inner planets, destabilizing asteroid and comet orbits, and potentially ejecting smaller worlds entirely. The solar system's current configuration represents billions of years of gravitational settling. One massive visitor would reset everything. Our solar system already possesses capture capability under specific circumstances. Research describes permanent weak capture where interstellar objects become trapped in the Sun's orbit through combined gravitational effects from both the Sun and the entire Milky Way Galaxy. The mechanism works when an object enters specific regions where the Sun's gravitational influence dominates, particularly around Lagrange points where gravitational forces balance in complex ways. The object initially follows a chaotic orbit, remaining unstable for extended periods before eventually settling into a stable, long-term path. Think of it like a ball rolling on a complex landscape with valleys and hills, eventually finding a stable valley to rest in. The Sun could theoretically collect passing rogue planets and hold them at the solar system's outskirts for millions of years, occasionally trading them with Alpha Centauri, our nearest stellar neighbor. It's entirely possible captured rogue planets already exist in our system's distant reaches, invisible and undetected. This brings us to one of astronomy's most intriguing mysteries. Planet 9. The hypothetical ninth planet lurking in our solar system's outer region has generated fierce scientific debate. Its existence remains unconfirmed, but the evidence supporting it keeps mounting. Astronomers noticed something peculiar about extreme trans-Neptunian objects, bodies beyond Neptune orbiting the Sun at distances averaging more than 250 astronomical units. These distant objects cluster in unusual ways. They tend to make their closest approaches to the Sun in one sector, and their orbits tilt similarly. Random distribution would create scattered orientations. Instead, they align. Something massive appears to be shepherding them gravitationally. Planet 9 would have a mass about 10 times Earth's and orbit roughly 20 times farther from the Sun than Neptune does. At that distance, it would take between 10,000 and 20,000 years to complete a single orbit. Astronomers Konstantin Batygin and Michael Brown proposed several origin scenarios. Perhaps Planet 9 represents a giant planet's core ejected from its original orbit by Jupiter during the solar system's violent youth. Or maybe we captured it from another star during a close stellar encounter billions of years ago. Here's where it gets interesting. Planet 9 might be a rogue planet we captured. The captured rogue planet hypothesis elegantly explains several puzzling features. First, the extreme orbital distance makes sense if the object originated elsewhere and was caught in a weak gravitational trap. Second, the tilted orbit relative to the solar system's plane fits better with capture than with formation in our protoplanetary disk. Third, the mass range matches typical rogue planets detected elsewhere in the galaxy. But finding Planet 9 has proven extraordinarily difficult. The Kuiper belt stretches vast and dark. Any planet at those distances would reflect minimal sunlight, appearing as an incredibly faint dot moving imperceptibly slowly against background stars. Astronomers have conducted large-scale sky surveys and targeted searches based on predicted positions. Both approaches have come up empty so far. Some researchers question whether Planet 9 exists at all. They argue the clustering of trans-Neptunian object orbits might result from observational biases. We discover and track these objects during limited portions of each year when they're visible from Earth. Perhaps the apparent clustering reflects when and where we're looking rather than real gravitational influence from an undiscovered planet. The Vera C. Rubin Observatory, currently under construction in Chile, will settle this debate. Starting operations soon, it will conduct comprehensive sky surveys with unprecedented sensitivity and coverage. Within a few years, Rubin will either find Planet 9 or definitively rule out its existence in the predicted mass and distance ranges. The waiting continues. Whether Planet 9 exists or not, the broader implications remain fascinating. Our solar system's architecture might not be as stable and unchanging as we once assumed. Planets can be captured from interstellar space. Giant worlds might lurk in the darkness beyond Neptune's orbit. The solar system we see today represents just the survivors of a far more chaotic past. What about conditions on rogue planets themselves? Would anything survive there? Without starlight, rogue planets exist in extraordinary cold and darkness. The outer layers, exposed directly to space, reach temperatures just a handful of degrees above absolute zero. At those temperatures, molecules barely move. Chemistry essentially stops. Any water would be frozen harder than granite. Atmospheres, if they existed initially, would condense and freeze solid on the surface, creating bizarre landscapes of nitrogen ice and frozen carbon dioxide. But deep beneath the surface, conditions differ dramatically. Planetary formation releases enormous heat. Large planets contain radioactive elements whose decay generates warmth for billions of years. Tidal heating from internal friction can add energy if the planet has large moons. These internal heat sources persist regardless of whether a star shines overhead. Scientists theorize that sufficiently large rogue planets might maintain subsurface liquid water oceans insulated by thick ice shells. Similar oceans exist beneath the ice covering Jupiter's moon Europa and Saturn's moon Enceladus, kept liquid by tidal heating despite surface temperatures around -200 degrees Celsius. A rogue planet's internal heat could sustain comparable environments. Could life exist in those dark oceans? On Earth, entire ecosystems thrive around deep-sea hydrothermal vents, completely independent of sunlight. Chemosynthetic bacteria derive energy from chemical reactions between vent minerals and seawater. Complex organisms have evolved to exploit these bacteria, creating food webs in absolute darkness. A rogue planet's subsurface ocean might host similar chemistry. Hydrothermal vents could form where the molten core's heat reaches the ocean floor. Dissolved minerals would provide chemical energy. Life wouldn't need photosynthesis, just chemistry. The same fundamental processes that began life on Earth billions of years ago could operate beneath a rogue planet's frozen surface. This possibility transforms our understanding of habitability. We've focused intensely on planets orbiting within their star's habitable zone where surface temperatures permit liquid water. But if life can exist in subsurface oceans heated by internal planetary processes, habitability extends throughout the galaxy. Every sufficiently large rogue planet becomes potentially habitable regardless of distance from any star. Billions to trillions of rogue planets wander our galaxy. If even a tiny fraction harbor subsurface biospheres, life might be far more common than we've imagined. The galaxy might teem with living worlds we can't even detect from Earth because they emit no light and reflect none from nearby stars. Detection remains the critical challenge. How do you find life on a dark, frozen world drifting through interstellar space? Traditional biosignatures like oxygen or methane in atmospheres don't work because rogue planet atmospheres freeze solid. Remote sensing can't detect subsurface oceans through kilometers of ice. Even if we identified a rogue planet passing relatively nearby, sending a probe would require decades or centuries of travel time. The best near-term hope might be detecting heat signatures. Large rogue planets with active internal geology should emit detectable infrared radiation. Future space telescopes optimized for infrared detection might catalog thousands of rogue planets based on their thermal emissions. Analyzing those heat signatures could reveal which planets likely maintain internal warmth sufficient for subsurface liquid water. Beyond detection, the philosophical implications stagger the imagination. If life commonly exists on rogue planets, it evolved in eternal darkness, powered by planetary heat rather than starlight. Such life would have no concept of day or night, seasons, or the sky. Their entire universe would be the ocean they inhabit, bounded by ice above and rock below. They would never see stars. Would such life develop intelligence? Could technological civilization emerge in a subsurface ocean with no access to fire, metals, or the night sky that inspired human astronomy? These questions remain purely speculative, but they challenge our assumptions about life's requirements and possibilities. The rogue planet phenomenon forces us to reconsider everything we thought we knew about planets, habitability, and our place in the cosmos. These worlds represent a hidden population potentially outnumbering conventional planets around stars. They demonstrate that planet formation is far more violent and chaotic than we imagined, regularly casting worlds into the void. They might harbor life in forms we've never considered, thriving in darkness and cold on chemistry alone. As detection capabilities improve and our catalog of rogue planets expands, we'll answer fundamental questions about planetary demographics, formation mechanisms, and habitability limits. The Nancy Grace Roman Space Telescope will provide unprecedented statistical data. Future infrared observatories will probe their physical characteristics. Eventually, we might even send probes to study nearby examples directly. The rogue planet story represents more than just astronomical curiosity. It's a window into the violent chaos underlying cosmic order. Consider what happens during planet formation. You picture a serene disk of gas and dust gradually coalescing into worlds. The reality involves gravitational warfare. Planets collide, merge, scatter each other like cosmic billiard balls. Some grow massive enough to dominate. Others get flung into the void at thousands of kilometers per second. Computer simulations reveal the brutality. Researchers modeled 100 planetary systems, each containing 3 to 10 planets in stable circular orbits around Sun-like stars. They ran the physics forward for 1 billion simulated years. Nearly every system eventually destabilized. Close encounters between planets triggered cascading chaos. The typical outcome: at least one gas giant ejected. 5 to 10 smaller rocky worlds cast into darkness. Our solar system probably followed this pattern. Evidence suggests we once had a 5th giant planet. During a chaotic period astronomers call late instability, gravitational interactions with Jupiter, Saturn, Uranus, and Neptune shifted this world's orbit. Eventually, those same giants exiled it completely. That lost planet now wanders interstellar space, a frozen monument to our system's violent youth. Binary star systems produce even more chaos. When 2 stars orbit each other, any planets face competing gravitational influences. Passing stars can perturb those wide binary orbits, occasionally sending the pair much closer together. The resulting gravitational turbulence ejects planets or even steals worlds from one star and gives them to its companion. More than half of all star systems are binary. The rogue planet production rate might dwarf single-star systems like ours. But here's where it gets stranger. Some rogue planets never orbited any star. They formed alone in interstellar space through processes resembling star formation. Collapsing clouds of gas and dust contract under their own gravity, accreting material directly from surrounding nebulae. They just don't gather enough mass to ignite fusion. Instead, they halt at planetary scales, becoming objects the International Astronomical Union calls sub-brown dwarfs. How do you tell these formation pathways apart? Velocity provides the crucial fingerprint. Ejected planets retain significant excess speeds, typically 8 to 16 kilometers per second. That's much higher than normal stellar velocities in star-forming regions. Planets ejected by binary star interactions move even faster, roughly 3 times the velocity of those scattered by planet-planet collisions. These measurements let astronomers reconstruct each world's origin story from its current motion alone. The numbers grow more staggering the deeper you examine them. Current estimates suggest 7 rogue planets per star in our galaxy. With 400 billion stars, that implies nearly 3 trillion wandering worlds. Some researchers propose even higher ratios, potentially 20 rogue planets per star. 8 trillion dark spheres drifting through the Milky Way. More planets floating free than orbiting stars. This fundamentally rewrites planetary demographics. We've spent decades cataloging exoplanets around other stars. Thousands discovered. Potentially billions waiting. But the true planetary population might lie hidden in darkness, vastly outnumbering conventional worlds. Most planets in the galaxy could be rogues. Recent discoveries confirm their abundance. In January 2026, astronomers announced finding a Saturn-mass rogue planet about 9,800 light-years away. What makes this discovery revolutionary? For the first time, researchers directly measured a rogue planet's mass rather than making statistical estimates. The observation combined ground telescopes and space instruments to triangulate distance and calculate mass with unprecedented precision during a microlensing event. Another 2025 discovery revealed truly bizarre behavior. A rogue planet designated CHA 1107 to 7626 sits about 620 light-years away in Chameleon. Its mass is 5 to 10 times Jupiter. And it's eating. This world accretes gas and dust from surroundings at 6 billion tons per second, the strongest accretion episode ever recorded for any planetary mass object. It behaves more like a forming star than a planet, with magnetic activity driving material infall in ways previously thought exclusive to stellar evolution. These discoveries raise profound questions about what defines a planet. If objects form through star-like processes but halt at planetary masses, are they really planets? If worlds wander freely never having orbited stars, do they count? Traditional definitions centered on objects orbiting stars. Rogue planets demolish those boundaries. The categories blur. We need new frameworks. Detection remains extraordinarily difficult. Rogue planets emit virtually no light. They reflect none from nearby stars because there are no nearby stars. Microlensing offers the primary technique. When a rogue planet passes directly between Earth and a distant star, its gravity bends the star's light, briefly magnifying its brightness. These events last hours to days maximum. You must monitor millions of stars continuously to catch them. Survey teams point telescopes toward Sagittarius, looking toward our galaxy's dense central bulge where 400 million detectable stars crowd together. Just 1 in 100,000 stars undergoes microlensing at any moment. You need massive statistical samples. In 2007, the OGLE project identified 611 candidate events. MOA found 488. Those numbers have grown as detection networks expanded, but identifying the brief signature of a planet within stellar microlensing events requires extraordinary precision. The microlensing light curve reveals mass, but distance remains approximate. When dealing with objects tens of thousands of light-years away, uncertainties span thousands of light-years themselves. You know a planet exists. You know its approximate mass. but pinpointing its location stays frustratingly vague. Everything changes with the Nancy Grace Roman Space Telescope launching by May 2027. This instrument images the entire sky 1,000 times faster than Hubble. Roman's Galactic Bulge Time Domain Survey should detect several hundred to several thousand rogue planets, providing the first comprehensive statistical census. The mission will employ both microlensing and direct infrared imaging, potentially finding worlds as small as Mars. Roman will also catalog the broader population of dark objects lurking between stars. Beyond rogue planets lie brown dwarfs, objects too massive for planets but insufficient for stellar fusion. Beyond those sit stellar corpses, neutron stars, and black holes. Astronomers estimate 100 million stellar mass black holes drift through our galaxy, but we've never definitively found one floating alone because they're invisible. Roman's mass-based detection will find them regardless of nearby matter revealing their presence. This comprehensive dark object census will answer fundamental questions about galactic structure. How much unseen mass fills interstellar space? How violent was early planet formation across the galaxy? What fraction of planets get ejected versus remaining in stable systems? These answers reshape our understanding of cosmic architecture. The threat assessment remains clear. Odds of a rogue planet entering our solar system within the next 1,000 years. Approximately 1 in 1 trillion. Space is incomprehensibly vast. Even with trillions of rogue planets wandering the Milky Way, distances between objects make close encounters vanishingly rare. The emptiness serves as natural protection. Our solar system remains effectively isolated despite the hidden population surrounding us. But what if? If a rogue planet did enter our system, consequences would depend entirely on mass, trajectory, and approach distance. A Jupiter-mass world passing through the outer solar system might only slightly perturb orbits. A super-Jupiter 13 times more massive could fundamentally reshape everything. Earth's orbit might become more elliptical, shifting us closer to the Sun during perihelion and farther during aphelion. Even without direct collision, orbital changes would prove catastrophic. Shorter, hotter summers. Longer, frozen winters. Growing seasons collapse. Food production fails globally. Civilization faces extinction not from impact but from climate chaos induced by gravitational perturbation alone. If we were unlucky enough to face direct collision. Complete annihilation. Both worlds vaporize. The energy release would match billions of nuclear weapons simultaneously detonating. Yet our solar system might already host captured rogues. Research suggests the Sun can permanently trap passing interstellar objects through a mechanism called permanent weak capture. Combined gravitational effects of the Sun and the entire Milky Way Galaxy can draw objects into chaotic orbits that eventually stabilize. These captured worlds might orbit at extreme distances, occasionally trading with nearby Alpha Centauri through complex gravitational interactions. Planet 9 could represent exactly this scenario. A hypothetical world 10 times Earth's mass orbiting 20 times farther than Neptune might explain the peculiar clustering of extreme trans-Neptunian objects. These bodies beyond Neptune orbit at distances averaging more than 250 astronomical units, and their orbits cluster suspiciously. Some astronomers propose Planet 9 was captured from another star. Others suggest it formed in our system but got kicked to distant orbits. The Vera Rubin Observatory under construction in Chile should either find it or definitively rule out its existence within years. Rogue planets force us to confront how little we actually know about our cosmic neighborhood. The galaxy contains hidden populations vastly outnumbering visible objects. Most planets might wander in eternal darkness. Some potentially harbor life in subsurface oceans heated by internal geology rather than starlight. We've built our understanding of habitability around stars, but the true story might unfold in places we can't even see. The darkness between stars isn't empty. It's filled with exiled worlds carrying the scars of ancient violence, drifting through the void as silent testimony to the chaos underlying cosmic order. Every planet we've ever studied orbits a star. Every definition of habitability we've constructed assumes stellar energy. Our entire framework for understanding planetary systems depends on gravitational hierarchies centered on fusion-powered spheres of plasma. Rogue planets demolish these assumptions completely. They represent a population potentially outnumbering conventional planets by factors we're only beginning to grasp. 8 trillion wandering worlds might drift through our galaxy alone. More planets floating free than orbiting stars. Most of the galaxy's planetary population exists in permanent darkness, following trajectories determined by violent ejections billions of years ago. Think about what that means for the search for life. We've focused exclusively on planets within habitable zones around stars, narrow bands where surface temperatures permit liquid water. But if large rogue planets maintain subsurface oceans heated by internal geology, habitability extends throughout interstellar space. Every sufficiently massive rogue becomes potentially habitable regardless of stellar proximity. Life on Earth began in darkness. Hydrothermal vents on the ocean floor supported entire ecosystems before photosynthesis even evolved. Those same chemical processes could operate beneath kilometers of ice on rogue planets, powered by planetary heat rather than sunlight. If even a small fraction of wandering worlds harbor such biospheres, life might be far more common than every optimistic estimate we've made based on stellar habitable zones. We'd never detect it with current methods. These hypothetical organisms would exist in sealed environments completely isolated from space. No atmospheric biosignatures to detect. No reflected starlight to analyze. Just dark frozen spheres drifting through the void, potentially teeming with alien chemistry in oceans we can't observe from trillions of kilometers away. The Nancy Grace Roman Space Telescope will transform this field when it launches. Hundreds or thousands of new detections. Direct mass measurements becoming routine rather than exceptional. Statistical distributions revealing formation mechanisms and ejection dynamics. Within a decade, we'll understand rogue planet demographics with precision currently impossible. But understanding population statistics differs dramatically from studying individual worlds up close. Sending probes to nearby rogue planets requires technology we don't yet possess. Interstellar travel at meaningful speeds remains firmly in the realm of theoretical physics. Even identifying which nearby rogue planets might harbor subsurface oceans presents challenges requiring infrared observatories we haven't built yet. The philosophical implications cut deeper than detection challenges. If technological civilizations can emerge in subsurface oceans on rogue planets, they develop completely different relationships with the cosmos than we have. No sky to observe. No stars to navigate by. No concept of day or night, seasons, or the broader universe beyond their frozen shell. Their entire cosmology would center on the ocean they inhabit, bounded by ice above and rock below. Would they ever develop astronomy? Could they even discover they existed on a planet without external reference points? The night sky inspired humanity's earliest scientific questions. What happens to curiosity about the universe when you live in eternal darkness with no universe visible? Our own solar system carries scars from the same violence that creates rogue planets. We probably ejected a fifth giant planet during late instability. The asteroid belt structure reflects ancient gravitational chaos. The late heavy bombardment that scarred the Moon resulted from orbital reshuffling among our gas giants. We're survivors of the same chaotic processes that filled the galaxy with wanderers. Planet 9, if it exists, might represent a captured rogue. Or perhaps a native world kicked to extreme distances. Either way, its potential presence reveals how dynamic and unstable even mature planetary systems remain. The solar system we observe today isn't frozen in place. It's a temporary configuration that will eventually change again given enough time. The statistical risk remains infinitesimal. 1 in 1 trillion chance of a rogue planet entering our solar system within the next 1,000 years. Space's vastness protects us far more effectively than any defense system. But the theoretical consequences illuminate just how delicately balanced our existence actually is. Earth's stable orbit within the habitable zone depends on gravitational architecture that took billions of years to establish. One massive intruder could reset everything. We don't need to worry about rogue planets destroying Earth. We need to understand them because they represent the majority of our galaxy's planetary population. They reveal how violent and chaotic planet formation actually is. They potentially harbor life in forms we never considered. They challenge every assumption we've made about what planets are and where they can exist. The darkness between stars isn't empty void. It's filled with worlds. Some larger than Jupiter. Others smaller than Earth. All carrying chemical signatures from their birth systems. All following trajectories determined by gravitational violence that occurred when their parent systems were young and unstable. They're monuments to chaos, frozen in time, drifting through the galaxy as permanent reminders that the ordered solar system we inhabit represents a rare exception rather than the cosmic norm. Detection methods will improve. Catalogs will expand. Eventually, we'll understand rogue planet populations with the same precision we currently understand exoplanets around stars. The Nancy Grace Roman Space Telescope starts this process. Future infrared observatories will continue it. Decades from now, we might even send probes to study nearby examples directly, analyzing their composition and searching for signs of subsurface oceans. But the fundamental revelation has already occurred. Most planets in the galaxy don't orbit stars. They wander alone through interstellar space, ejected during the violent formation of planetary systems or formed independently in collapsing gas clouds. The universe contains far more dark worlds than illuminated ones. We've spent centuries studying the exceptions while remaining completely ignorant of the rule. Rogue planets aren't anomalies. They're the norm. The galaxy is filled with orphaned worlds drifting through darkness, and we're only beginning to understand what that means for planet formation, the prevalence of life, and our place in a cosmos far stranger than we imagined.